Okay, so today we'll discuss about the topic is about the transmission of heat. Always heat energy flows from the high temperature to the low temperature. Always. But it transfers, okay, the heat transfers in the three modes. Conduction, one is the conduction. And other one next, the second is the convection. Next is the radiation. Now, in case of conduction, medium is required. In case of convection, medium is required to transfer the heat energy. To transfer. In case of radiation, medium is not required. Medium is not required. Now, in case of conduction, one more point is that in case of conduction, particles will not move. In case of convection, particles will move. Here, no particle at all. Okay. Now, today we'll discuss about the conduction. In detail, we'll discuss afterwards about the convection and radiation. Okay. Today's topic is about the conduction. Okay. In the conduction process, energy transfers from one point to another point, high temperature to low temperature, without motion of the particles, matter. Heat energy travels from high temperature to low temperature. High temperature to the low temperature. Without motion of the particles. Now, in this case, here medium will not move. Suppose okay, here was suppose to consider any rod or any conducting material. But this one point is at high temperature theta1. Other point is temperature theta2. Here theta1 is greater than theta2. Because this is the area, one area. We consider as this one area. Excuse me. Here, these two are the parallel surfaces. Here, A is the area for each surface. Here, L is the length of the conductor. Now, here, what this is the high temperature is at low temperature. Now, actually, this conduction takes place only in the solids. Suppose if we take a semi-solids, conduction not possible. In case of liquids, also no conduction. Only in case of solids only it takes place. Only in solids. Now, How the energy will travels in this case, we'll discuss. Okay, energy will travels from the high temperature to low temperature. Assume that Q is the energy travel. The rate of heat transfer is heat transfer rate. Okay, I'm writing as a Q by T. Q is the energy transfer in T seconds from one end to the other end, which is proportional to the area cross section, and proportional to that means temperature difference. More is the temperature difference, more heat energy will travels. And inversely proportional to length of the route. That's okay, sir. If more is the area, more energy will travel. More is the temperature difference, more energy will travel. More is the length, what happens that less energy will travel from one end to the other. Now to remove this proportionality, remove the proportionality symbol, we'll get actually a Q by T is proportional to the so the area, temperature difference. Inverse proportional to length. Just to remove the proportional symbol, multiply it on K. K is called here K like this. Proportional constant. Here K is the coefficient of thermal conductivity. Proportional to constant K is the coefficient of thermal conductivity. Now here Q by T is the rate of heat flow. A is the area of cross section. Theta 1 minus theta 1 and theta 1 minus theta 2 is temperature. Here you can write the expression for the K as like this. K you can write like this. Q by T. Where Q by T is the rate of heat flow. The whole divided by area into theta 1 minus theta 2 divided by L, we can write like this. Here Q by T is the rate of heat flow. A is the area of cross section. Here we can say that theta 1 minus theta 2, theta 1 minus theta 2 is the temperature difference. Suppose if you take the ratio of these two, temperature difference length ratio is called the temperature gradient. Now, from this one, we can say that we can define K as rate of heat flow per area per unit temperature gradient is called the coefficient of thermal conductivity. We can define like this. per unit area. Sorry, due to loss of net connection. Just a minute. Hello, sir. నెట్ పోయింది సార్, మళ్ళీ మొబైల్ ఆన్ చేస్తున్నా సార్. అవును, అర్థమైంది సార్. అది మొబైల్ ఆన్ చేస్తాను. Oh, here, look here. So we got this one. 2 by rate of heat flow can written as K into area into theta 1 minus theta 2 divided by F. Here K is the coefficient of thermal conductivity. Now we can write the expression of K like this. Two by T divided by 1. Now here Q by T is the rate of heat flow. Now here we can say that theta 1 minus theta 2 by L is that the ratio of the temperature difference to the distance to the 2 points. This is the temperature gradient. This is called the temperature gradient. Now A is the area of cross section. Now we can define this one as like this. Definition of K can be written as, we can say, rate of heat flow per unit area per unit temperature gradient. Is the definition. Rate of heat flow per unit area per unit temperature gradient is the coefficient of thermal conductivity. Now, if the K value is more, we can say that the conductivity of the material is more. K value is less, conductivity of the material is less. Suppose if you take silver and copper, they will have the high K value. If you take the wood, for silver and copper, high K value. For wood, And for plastic or for rubber, the K value will be the less. If the K value is less means what? Those are the bad conductors. The K value is high means those are the good conductors. Now next, in all the cases, this formula is not applicable. This expression is applicable only in case of steady state. This formula is applicable only in case of steady state. Steady state means the temperature gradient should be at any point, suppose this is a rod. Take any 2 points along the rod and take the length. Suppose the length is this is the delta L. Temperature difference is delta theta. Always delta theta by delta L, which is for the temperature gradient. Temperature gradient should be constant. And the next one is the rate of heat flow should be constant. dQ by dt. Rate of heat to be constant. To be constant through any cross section area. Take any place at any place. Suppose here between the 2 points we consider here and here. At every point the rate of heat flow should be the same. Then only we can say the steady state. And the temperature gradient should be constant. Next is laterally there should not be any heat flow. The heat flow should be between the two parallel surfaces. Between the parallel surfaces. Okay, these are the conditions for the steady state. In case of steady state only, it is this formula is applicable. There should not be any heat flow through the lateral surface. Like this, heat should not flow in this direction. In this case, this formula is not applicable. The heat flow should be only along this direction, between this surface to this surface. In this case only, the whatever we discussed, that formula is applicable. The coefficient of thermal conductivity also can be defined. Okay, actually in the JEE level, only we are having only steady state condition only we are having. Okay, some cases the rate of heat flow may not be steady. That case we are not having the syllabus. That's why no need to discuss that concept. Okay. Now this is the rate of heat flow. The expression also we understood. Okay, we discussed. Next about the temperature gradient I discussed. Generally they have lost the problems on temperature gradient also. Just now I told temperature gradient means what? The ratio of temperature difference between the 2 points to the distance between the 2 points. Otherwise, we can say that delta theta by delta L, which is the temperature gradient. Temperature gradient. Now, the ratio of these two is called the temperature difference between the 2 points to the distance between 2 points is called the temperature gradient. It should be which is equal to constant. It is constant in a particular problem. Now, based on these problems are like that they have lost. Example, I will give one problem. Suppose one rod is this is one rod. Now here is the temperature is some 200 degrees centigrade is at this end temperature. At the other end temperature is the 20 degrees centigrade. The energy flowing from this 200 degrees centigrade to 20 degrees centigrade. And here length of the rod is 1 meter. 1 meter is the length of the rod. Now there will be the data like this. Now I want to find out the temperature at a point at a distance. This is here the 0. Okay. At a distance 20 centimeters. At a distance 20 centimeters, I want to find out the temperature. Here I want the temperature. The point is there at a distance 20 centimeters. At this point, I want to calculate the temperature. Okay, actually here what the main thing is the temperature gradient is constant. According to this concept, in the study state, temperature gradient is constant. Now here temperature gradient is the delta theta by delta L is the temperature difference is 200 minus 20 divided by length is 1 meter. Okay, if you take in the meter, something like that, around 1 meter. Now, which is equal to the, I will consider this is 1 point is another point. In the first case, I consider this is a 1 point is another point, second point. That's why temperature difference is 200 minus 20. Distance between the 2 points is 1 meter. Now I will consider this point and this point. Now temperature difference becomes 200 minus theta divided by. Now distance between the 2 points is the 20 centimeters. 20 centimeters nothing but 0.2 meters. Now just by doing the cross multiplication, we can calculate theta. Suppose we do the cross multiplication. Okay, 200 minus 20 is the 180. 0.2 into 180 is equal to 200 minus theta. Now theta becomes 200 minus, this becomes how much it is? This becomes 36. 0.2 to 180 is 36. It becomes this value is 160. Means at a distance 20 centimeters from 200 degrees centigrade, the temperature of the rod is 164 centimeters. Here what happens that according to the temperature decreases from the one higher and descend to the this side. The rate is that's always the temperature gradient is constant. Okay, in this way we can calculate the temperature of dot at any position. We can calculate. If you know the temperature gradient, otherwise okay, this is a hot end and cold end temperatures. If you know, we can calculate the temperature at any point of the rod. This is one. This is the problem about the temperature gradient. Now, next topic is I will discuss about the thermal resistance. Now, before discussing thermal resistance, one thing you should know: heat energy flows from the high temperature to low temperature. We know, and the current flows from the high potential to the low potential. Electric current flows from the means charge will move from the high potential to the low potential. And similarly, air flows from the air or gas will move from high pressure to the low pressure. Water flows from the high to the low down. Heat energy flows from the high temperature to low temperature. Now I will take the analogy of the electricity. Using that one, I will calculate the resistance expression for the thermal resistance. With the help of analogy, we can easily derive the expression for the thermal resistance. Now, I'll discuss electrical. Okay, electrical to the thermal. I'll discuss. The thermal transmission, electrical phase. Current, thermal current to the electric current to the thermal current. In case of electrical current, we can define that the potential difference is defined as the V. According to Ohm's law, V equal to I to R. I is the rate of flow of charge, otherwise current. I can be written as V by R. I is the rate of flow of charge, dq by dt. R is a resistance and V is the potential difference. PD. PD is a potential difference. V is R is a resistance. Electrical resistance. Now, I can write as V by R. Similarly, in case of thermal transmission, heat transmission, I is analogy to the rate of heat flow. We can write the dq by dt. Can be written as V is the temperature difference. The analogy for the V is the temperature difference, theta 1 minus theta. Actually, expression for dq by dt is the k into theta 1 minus theta 2 divided by A into area also. Now, same formula you can write like this. Theta 1 minus theta 2 divided by L by K. L divided by K into A. So this is very important. Thermal resistance is very important. Now here, analogy, if you take, you can observe the analogy. Analogy means similarities. For I analogy, I is the current in the thermal transmission or heat transmission, dq by dt. It's a rate. Okay. Instead of I, we write dq by dt. For V is the here, V is the potential difference. Here we will take it as theta 1 minus theta 2. Next, R is the resistance. Now in this case, R is a L by K. Here L by K is called the thermal resistance. The thermal resistance, R is called thermal resistance. L by K. Okay, finally we can conclude that the thermal resistance of the rod is proportional to the length of the rod and inversely proportional to the area of cross section of the rod and coefficient of thermal conductivity. This is the expression for thermal resistance. One should know the thermal resistance expression. But this is about thermal resistance. Now, next topic is if the different slabs or different conducting materials are connected in the series and parallel, how the rate of heat flows, how to calculate the effective thermal conductivity. Okay, if you want to copy this one, copy this page. Now, first I'll discuss when rods are connected when different rods are connected in the series. Excuse me. Just a minute. Now, rods connected in the series. If the rods are in the series, suppose two different rods are there. One rod. Next is another rod. Okay. I think both are in the same area of cross section. Now, A is the area of cross section of each rod. L is the length of each rod. Now, K1 is the thermal conductivity of the first rod, and K2 is the thermal conductivity of the second rod. Now, in this case, how to calculate effective thermal conductivity? Assume that R1 is the resistance of the first rod, thermal resistance, R2 is the thermal resistance of the second rod. Now, we can write R1 can be written as L by K1 into A. R2 we can write like this, L by K2 into A. There one thing you have to observe. Assume that heat energy flowing from this side, the left side to the right side. Is it a high temperature, low temperature? Now suppose the two pipes are different pipes are connected in series. Whatever the water will enter at one end, the same amount of water will leave the other end. Here also same thing. Whatever the energy is flowing through one end, the same amount of heat energy will leave this other end. In this case, in the series, what happens? One point you should know. dq by dt will be the same at any point, any cross section. Rate of heat flow. dq by dt, nothing but rate of heat flow is same at any point. Now, suppose here the temperature is T1, the temperature is T2, the temperature is T3. Now, when the two different rods are there, if the first rod temperature gradient will be different, here second rod temperature gradient will be different. But rate of heat flow will be the same. Now, in the first rod, rate of heat flow will be T1 minus T2. Okay, rate of heat flow we can write like this. Temperature difference by thermal resistance. I'm writing like this. R1 I'm writing. The second rod, temperature difference is T2. Okay, T2 minus T3. Divided by R. Now, using this expression will help while solving the temperature at the junction where the both the rods are meeting. At that point, to calculate the temperature, it will help. Next one is how to calculate the effective thermal resistance. Here, all the rods are connected in the series. Now, in this case, assume that K is the effective thermal conductivity. KE. Uh, 12 becomes the length, effective length. Total length of the rod becomes 12. And the area A is the area of cross section. Now here one point is the rate of heat flow throughout both the rods will be the same. Now here one point you should know. We can write T1 minus T3 can be written as temperature difference. If you take the temperature difference, T2 minus T1. Sorry, T1 minus T2 plus T2 minus T3. Now we can write the T1 minus T2. Okay, just just a minute. We are having the formula. I'll turn the page. Basically, this is a dq by dt is the rate of heat flow. You know, dq by dt is the first case, means dq by dt can be written as, okay, so like this effective is a k. K is the area of cross section. T1 minus T3. Total length is a 2L. From this one, we can write T1 minus T3 can be written as temperature difference expression can be written as dq by dt into 2L by K. Same thing I will substitute. Okay, in the equation, this equation. In this equation, I will substitute. Now we can write this one as T1 minus T2. We can, sorry, T3. Excuse me. T1 minus T3 can be written as dq by dt into 2L divided by K. Okay, so next point, this point can be written as T1 minus T2 can write like this. dq by rate of it for the first rod is also dq by dt1. And length of the rod is L. K1 is the thermal conductivity, A is the area of cross section. Yes. L is the length, K2 is the thermal conductivity, A is the area of cross section. Now here dq by dt is same, that's why we can cancel. Okay, finally after solving this one, we'll get 2 by K equal to 1 by K1 plus 1 by K2. This is one equation we get. In the series combination, we can calculate using this formula, using this method. Your formula is not important, method is important. Using this method, okay, you can calculate the effective thermal conductivity. And one more thing also we can say, same equation can write like this also. You know, effective thermal resistance is R. R can be written as L, effective length is a 2L, 2L by Ka. R1 is a L by, you know, R1 is a L by K1, K1 into A. R2 is a L by K2 into A. Okay, the series we can write like this. Effective thermal resistance can be written as R can be written as R1 plus R. Okay, even in case of electricity, current electricity also same thing. Effective resistance is in the series combination is R equal to R1 plus R. Even in case of thermal conductivity also same expression only. So this is a series combination. Okay, I hope you understood. Now next one is when the rods connected in the parallel. And one thing you should know, in the series combination, what you have to remember is when rods are connected in the series, otherwise two different plates are connected in the parallel in the series. Means side by side they kept. Means that we can say that they are in the series only. This point you should know. Temperature difference between the, okay, across each rod two resistance, the ratio of these two should be constant. Means the rate of heat flow is constant, means this will be constant. This equation will use, and this equation also will use. But these two are the important equations. The series combination, this equation will use to solve the problems, and the rate of heat flow is constant, but this equation also will use. Okay, this formula is applicable only to calculate K. It's not important, it's a method only. But especially this is very important, R equal to R1 plus R2. Okay, these equations should know. Main point is the rate of heat flow is constant. That is the main point in the series combination. Based on that one, we can solve any problems we can solve. Now, for example, I'll discuss one problem. In the series, suppose one rod is a first one rod. Second rod. Here K is the thermal conductivity. Here K2K is the thermal conductivity of this rod, second rod. Now, L is the length of the rod. To calculate effective thermal conductivity means directly you can apply 2 by K effective, you can written as 1 by K1 plus 1 by K. Okay, using this one, you can calculate the effective K. It's very simple. That is simple one. No, it's not issue. Suppose if they are asking the temperature at this position. Suppose here is a theta1 is the temperature at this position. Theta2 is the temperature at this position. And theta3 is the temperature at this position. Suppose I don't know theta2 means so this is on take as of theta. So this theta. How to calculate the value of theta? My question is effective thermal conductivity, you can calculate this one using this formula is not a simple one. But here how to calculate the temperature at this position? Here the temperature is theta1, here other end temperature is theta3. At the junction temperature is theta. Thermal conductivity the first order is K, second order is 2K. In here, how to calculate temperature at the junction? But the main concept in the series combinations, the main thing is the rate of heat flow will be same. d2 by d2 should be constant, should be same. Means because the rate of heat flow in the first rod should be equal to the rate of heat flow in the second rod. Both are same. Now in the first rod, rate of heat flow becomes temperature difference by thermal resistance. Okay, it becomes theta1 minus theta divided by L by K. Here L by K is the thermal resistance. Now here, in this second rod, temperature difference is theta minus theta divided by thermal resistance becomes L by 2K. Now we can by cancelling the L and K and A, we will get the after solving this one we will get theta1 minus theta into Ka by L, which is equal to the theta minus theta3 into 2Ka by L. Okay, so after cancelling this one, you will get cancel the, you can calculate the theta. Ka get cancels. L also cancel. So theta will be there. Now if you write theta this side, then theta becomes theta1 plus 2 theta3 divided by 3. This is the temperature of the junction. This is a procedure, but answers are not important. Rate of heat flow is the same. They using this concept only we solve the problem. This is the approach. Now next one is the next like this type of problems will be there in the series combination. Next I will discuss the rods connected with the parallel. This is one rod. This is another. Both are side by side. Both are on the same length, same area of cross section. Here temperature, here is the temperature is T1 here at one end, the other end temperature is the T2. Now K1 is the thermal conductivity of the first rod and K2 is the thermal conductivity of the second. Now in the parallel combination, one point you should know. Temperature difference across each rod will be the same. Delta T. But rate of heat flow will be the different. Now total rate of heat flow will be the dq by is the rate, total rate of heat flow. dq1 by dt is the rate of heat flow through the first rod. dq2 by dt is the rate of heat flow through the second rod. Now again we will use the same form, this formula, rate of heat flow formula I will use. dq by dt equal to actual form, this is a k into area into temperature difference, delta T right here, temperature difference. Delta T divided by. Now, total rate of heat flow to consider. Assume that K effective is the K effective I'm taking. Now, affected area is the here. Temperature difference is T1 minus T2. L is the length of it. Rate of heat flow through the first rod. If you consider first rod, K1 is the thermal conductivity, A is the area of cross section. T1 minus T2 is the temperature difference. L is the length of it. Plus dq2 by dt. K2. A is area of cross section. Temperature difference is T1 minus T2. Here we can cancel the T1 minus T2. It will be common one. Now you will get 2K into QL by A. Now in this case, what happens that A get cancels. Okay, now here L also get cancels. You can write, you will get K effective can be written as K1 plus K2 divided by 2. Okay, this is the method to find out K. Don't consider this is only the formula. Why? Because sometimes there will be the different areas and different areas in you. Parallel means compulsory both will have the same length only, but areas may be different also. That's why you should follow this one. This is the main point. The rate of heat flow means sum of the total rate of heat flow will be equal to the Sum of the rate of heat flows through each rod. And the next one is the temperature difference should be constant. Based on these 2 points only, the problems can be solved. Next, one more thing is you'll get, R is L by Ka. L by 2A into K is nothing but effective resistance. That's why it becomes 1 by R. The parallel form 1 by R equal. There it becomes 1 by R1. So 1 by R. Here R1 is the R is the effective resistance, is the effective thermal conductivity is the L by 2 Ka. R1 is L by K. L by K1 into R2 will be the L by K2 into. So here one thing you have to remember this. Delta T will be the same in the parallel combination. And the sum of the total rate of heat flow will be the sum of the rate of heat flows through each route. Based on this one, these 2 points, we have to solve the problem. The another point is this is 1 by R equal to 1 by R1 plus 1 by R2. This using this one also, this formula also is okay. This is the case when the rods connected in the parallel. Now, sometimes what happens that there will be the different rods. Some rods in series, some rods in parallel. So we solved the problems in the resistance problems in this one, current electricity. Similar here also we can solve the problem similar way. Suppose one rod is there. First one rod is connected like this. The one more rod is connected like this. The next for this one more case like this. Some rods series and parallel. K is the thermal conductivity of this rod, and one more rod also connected like this. Same okay. 2K is the thermal conductivity of the rod, this rod. Same length and same area of cross section. So this rod also same length and same area of cross section. And here 2 more rods are connected like this. Here again 1 more rod like this. Again this is having the K. This one is having the 2K. This rod is having the 3K. Like this. Now in this case, they will ask what is the effective resistance of the rod. Again, this rod also have the same length, same area of cross section. This rod also have the same length and same area of cross section. This rod has the length L and area of cross section. Now, how to calculate the effective resistance and effective thermal conductivity? First, we'll discuss the effective resistance. How to calculate the effective resistance or net resistance? Okay, look here. Here, first 2 rods are the series. Again, this one and this one in the parallel. Again, this combination series with the third rod, like this. Now we can consider like this different the different rods connected like this. This is R1, R, R3, R4. This is R. These are the series means R1 plus R. Here this is in the parallel. Now effective becomes R1 plus R. Sum of these two. Again, effective ratios of this portion becomes R3 into R4 by R3 plus R. Again, this is in series. This is R5. Basically R is L by K, thermal resistance. R1 is L by Ka. R2 is K is to L by 2K. Again, R3 is L by Ka. R4 is L by 2Ka. In this way, you have to substitute each and every point, every that value according to this formula, and you have to simplify. Okay, I think it is simple, just like a current electricity problem, but only it takes a lengthy calculation, substitution. Okay, we can remove the common terms L by K, L by L, you can cancel. After cancel, we will get the easily depends on the point. Take the L by K common, then it will be easy for me. To take the L by K common full equation, you can solve the problem easily. Quadratic full step. L by K is common in every place. That's why it's 1, it becomes 1. 1 plus 1 by 2. So again, this is a 1 into 1 by 2. Divided by 1 plus 1 by 2. Again, this plus R3 L by K. Okay. 1 by 3 it becomes. Now it is very simple. Now we can simplify this equation. Okay. Such type of problems they will ask the JEE mains. Such type of questions you will get. Now, okay, this is about the series and parallel combination. Now, next one is the Kirchhoff rules also applicable in this case, thermal conductivity. In the thermal conduction, Kirchhoff rules also applicable. Kirchhoff rules. Next topic is about the Kirchhoff rules. How to apply the Kirchhoff rules in there. The first rule. We'll discuss most of the problems are based on first rule only. Okay. Yeah, what about why? Because loops are not there in this one, thermal conductivity. We studied, suppose at the junction, sum of the entering currents, I1, I2 are the entering currents, I3 and I4 are the leaving currents. Kirchhoff first rule is the sum of entering current equals sum of leaving current. Now we can say that here I1 plus I2 equal to I3 plus I4. Sum of entering current equals sum of leaving. Similarly, we can solve the problem here also. In the Kirchhoff rule, for example, some different rods are there. Okay, L is the length of the rod, A is area of cross section, K is the thermal conductivity of this. Okay, here also this is rod down, L is the length of the rod and A is area of cross section. 2K is the thermal conductivity of this rod. Suppose at this point temperature is some 100 degrees centigrade. The temperature. And here the temperature is some 20 degrees. Here is a 20 degrees centigrade the temperature. And this junction is connected to some other rod. Here length is L, A is area of cross section, and 3K is the thermal conductivity of this rod. But here temperature different. Here temperature is 10 degrees centigrade. Now, no doubt, is at high temperature. This 20 degrees or 10 degrees are low temperature. That's why as a result, what happens? The heat energy flows like this, and from here to it will flow like this. Like this. This one I will consider as I1. This is I2, and this is I2. You can write equation as I1 equal to the I2 plus I3. Here I am considering that I is a thermal current, dq by dt. Thermal current is dq by dt. Now, how to calculate junction temperature? Suppose this theta is the junction temperature. How to calculate theta at this position? The 3 rods are there like this. This one is the 100 temperature, this end, here 20, here 10. 3 rods are different rods. All the rods are the same length and same area of cross section. Only thermal conductors are different. This rod having the thermal conductivity K, this rod having the 2K, this rod is having the 3K. You know, current nothing but temperature difference with thermal resistance. Assume that our resistance of this one is R1. Now we can write this one as temperature difference is 100 minus theta. By R1. Okay. Second rod. Temperature difference is the theta minus 20 divided by R. Now here the third rod temperature difference is theta minus 10 divided by. This model is very important here. Now you can calculate R1 is the L by R is the L by K. Now we can write like this: 100 minus theta. R1 is L by K. Theta minus 20. L by 2K. Yes. Theta minus 10. L by 3K. Now L by K get cancels. Finally, you will get 100 minus theta will be is equal to the 2 into theta minus 20 plus 3 into theta minus 10. Now using this expression, we can calculate theta. This is one of the important model in the thermal conductivity based on the Kirchhoff rule. Okay, make a note of this problem. You'll get the approach how to solve this type of problems. Next topic is the next discuss. Okay, just great. Okay, I'll give one more problem based on the Kirchhoff rule. One more question. point A, this is the point B, this is C, this is D. Okay, thermal conductivity. Okay, so look here. The resistance of this one is one rod. This first rod is X here. This rod also X. This rod also X. This rod is Y. This rod is Y. Even this rod also Y. Means these okay, BC, CF, and FE are EF. Sorry, similar same rods. And the AB, BD, and the D are the same rods. Now, suppose if the temperature of if the temperature of the A and F, here is A, temperature of A is the 100 degrees centigrade, and temperature of F is the 20 degrees centigrade. Now, in this case, how to calculate the temperature at B and E? How to calculate temperature at B and E? I mentioned that A and F are given 120, but I'm asking the temperature at B and E. Now, in this case, how to solve the problem? I'm asking temperature at B and E. That's why I'll consider this whole thing as a one point, one section, one rod, and I'll calculate effective resistance. Now, resistance of this AB. Okay, so here look here, thermal conductivity here. The ratio between okay, thermal conductivity is this is having thermal conductivity. X is having thermal conductivity K, and the Y is having thermal conductivity K by 2. The rod X is having thermal conductivity K, the rod Y is having thermal conductivity K by 2. All the rods are identical. My question is, what is the temperature at B? And what is the temperature at E? I'll do one thing. AB has a one resistor like this. You can solve. You can write these two are in the series. These are in series. You know, this is the point A. This is the point F. This is the point B. This is E. You know, thermal resistance of this one. Okay, suppose you know formula for the R equal to L by K. Thermal resistance. Now here, thermal conductivity of the Y is K by 2. X is K. I do. Now then, what happens that suppose the AB resistance is R. Now in this case, we can say that the resistance of the X becomes Rx becomes. Suppose if it is R, then Ry becomes 2R. Why? Because thermal conductivity of this Y is K by 2. That's why it becomes 2R. This is R. This is the 2R. This is also 2R. This is R. This is R. The resistance of this part also 2R. Now first calculate the look here. I'm asking my interest is finding a of temperature B and A. That's why I'll replace this whole part as a between the B and A single rod, single resistance. These two are in the series, these are in the series. But again the combination is parallel. This is the 4R. This is 2R. This is a point B. This is a B E. This is A. This is 2R. This is the sum of this is the 4R. Effective ratio between these two ends is the 2R. Again, 2R and 4 are in the parallel. Now it becomes point A. The effective ratio becomes 2R into 4R by 4R plus 2R. Then it becomes 4R by 3. It's a point. Is a point B. This is a point E. This is a point F. Again, this relation is this is the 2R. Now we can say these three are in the series. The series rate of heat will be the same. The temperature of this one is a TB. This is TB. Okay. Now we can write you will get the different rate of heat will be same to any this one. Temperature of A is 100. 100 minus TB. Divided by R, which is equal to TB minus TB. Ratio is 4R by 3. Next. TB minus F. F temperature of F is 20. By 12. Now, if you equate these two, one set of equation will get. Equate these two, you will get another set of equation. The two unknowns are there, TB and TE. By solving the two equations, you will get the TB and T. That's all. Okay, this is one of the important, very important question. Here, TXXX. The rod X is having the ratio, thermal conductivity K. The rod Y's are having thermal conductivity K by 2. All the rods are in same length and same area of cross section. The ratios of the rod X is or rod Y is that it becomes 2R. Y becomes K by 2. Now these are the like series and parallel. These are the series, again they are parallel like that. Our interest finding out temperature at this point in time. That's yeah. Okay. By equating these two, you get one equation. By equating these two, you get another equation. By solving the two equations, you get the temperature at the this one. The TB and T both you get. The TB and T are the two unknown values. Okay. By equating these two means 100 minus TB equal to 3 into TB minus TE by 4. First equation. Second equation is the I'll do on the instead of these two, you can equate these two also, you can equate easily. The fraction is there. Otherwise, you can equate these two also. You can. Okay, solve the two equation 1 and 2. First equation, the second equation. Solve the equation 1 and 2. We'll get the TB and T. That's all. Now, the problems based on the Kirchhoff law will be like this. Now in the thermal conductivity, one more concept also very important. One important concept is that is the cold countries like Kashmir, or if you take European countries or Canada, the cold in the winter, what happens that on the lakes, ice formation, ice will form. Day by day, what happens, the thickness of ice increases. Now in that case, how to calculate the growth of ice? Okay, growth of ice on ponds or on the rivers in cold countries. Based on the thermal conductivity only, we can solve this problem. Growth of ice. On water. Now, suppose this one pond is generally here. What happens that in the pond case at any place after the rainy season, winter will start. Generally, anywhere in the rainy season, the temperature will be at 10 degrees centigrade, like 20 degrees centigrade. Even in the cold countries also, in the rainy season, temperature is 5 degrees, like the 20 degrees on. Now, when winter starts, okay, means that the rainy season temperature is 10 degrees. Means full water temperature also 10 degrees centigrade on, approximately. Suppose winter started. In the winter, what happens that like Canada, if you take it, it becomes minus 40 degrees centigrade. In the Kashmir means in the minus 5 degrees like that. Suppose minus 10 degrees centigrade is the temperature. What happens that water temperature is 100 is at 10 degrees centigrade. The heat energy flows from this bottom to this water to the surroundings. The beginning, what happens that first the top layer temperature decreases, energy flows from here to here. The temperature of this one decreases. Initially, the water is at 10 degrees centigrade. Temperature of 10 degrees decreases. As a result, what happens that for a water liquid, as the temperature decreases, density increases. The low temperature, suppose it decreases to 8 degrees centigrade. The 8 degrees water goes to the bottom, and 10 degrees water reaches the top. In this way, from bottom to the top, energy will flow. Particles will move, the heat energy will be traveled. But the water having the one peculiar behavior, anomalous behavior of water. At 4 degrees centigrade, water has density of water is maximum. That's the one peculiar behavior of water. Anomalous behavior of water. At 4 degrees centigrade, density of water is high, maximum. Now, when the lake temperature reaches the 4 degrees centigrade, what happens at bottom temperature of 4, here also 4 will be there. After 4 degrees onwards, its temperature decreases to 4 degrees centigrade, 3 degrees centigrade, slowly as the time passes. Why? Because outside is minus 10, energy is traveling from water to the surrounding, temperature decreases. Bottom temperature will be 4 degrees centigrade. Bottom decreases to 3 degrees centigrade, but 3 degrees centigrade density will be the less only. Less denser particle will be the top only. Finally, what happens that at one moment, the temperature of the top becomes a 0 degrees centigrade. Bottom is a 4 degrees centigrade, here is a 0. Okay, slowly temperature, okay. Still, okay, this is minus 10. Still, energy flows from 0 degrees to minus 10. Okay, suppose the water is at 0 degrees centigrade. If you remove the energy from that water, it converts into ice. As a result, what happens that here ice formation starts. Converting to ice. Here is a minus 10 degrees centigrade. This is at 0 degrees centigrade. Even the energy is traveling. This is at high temperature, low temperature. Ice is a bad conductor of heat. But bad conductivity is very low. K value is low. Energy slowly travels. Energy, when as the energy travels, what happens from inside to the outside, the ice will condenses. Water converts into the ice, right? Slowly, the thickness of ice increases. But what happens that ice is a bad conductor. Once some thickness is formed, next step what happens is very little energy will flow from the inside to the outside. As the time passes, the energy travel from thickness increases. The energy travel from the inside to the outside is very low. The rate of heat flow will decreases to very low value. As a result, what happens that throughout the winter will be there 3 to 4 months in the winters in the cold countries. Bottom temperature will be 4 degrees centigrade. Only at the top, only the ice layer is increasing. Finally, what happens? Finally, the aquatic life will be safe at the under the water. But here only at the top, what happens? Ice layer will be the thick ice layer. The persons can move and they can play also. Person can also move on the ice layer. Now, in this case, how to calculate this increasing of ice? How the this one, growth of ice? At what rate the ice will increase? That point that is very important. That I'm going to calculate. Now, calculate the growth of ice. Outside here is a temperature is the case 0 degrees centigrade. Is that minus theta I'm taking, outside temperature minus theta I'm taking. Not for example, I took minus theta, but now I'm taking theta. Minus theta. Minus theta. And here the temperature is the 0 degrees centigrade at the bottom. Here under the water ice. Now assume that when the ice is the thickness of ice is y is the thickness of ice. Right. Y is the thickness of ice. Now, and the dy is the ice formed in dt seconds. Thickness of ice form. Okay, dy is the thickness of ice form in the dt seconds. dt, the time dt. Now, basically again we'll use the formula of this one, and the rate of heat flow from inside to the outside surrounding temperature is the dq by dt equal to k into a into temperature difference is 0 minus theta. 0 minus theta. Divided point. Thickness is here y is the thickness. Now how to solve? dq by dt. The energy travel, suppose with the in the latent of, suppose L is the latent of ice, we can say that the energy travel from inside to the outside can be written as dq can be written as dm, mass of the ice converted to ice, water converted to water, m into L ice. L ice is the latent of ice. Formula one formula is there. The specific heat of dq equal to, suppose when water is converted into the ice, the energy travel from the water, transfer to the from the water is, and the energy lost by the water can be written as dq equal to m into ls. When the water at 0 degree centigrade converted to ice, the energy lost by the water equal to the m into ls. This formula we use this. dq can be written as dm into ls. dm is the mass of the water converted to nothing but volume into density. Volume of the water converted to ice is the thickness is dy. divide into area of cross section into the volume into rho is the density. LS. Okay, instead of dq, I'll substitute this by. Now in this case, now we'll get d1 to a into rho into LS divided by dt is equal to k into a into 0 minus theta becomes theta. Here a get cancels. Just copy this page. I'll wait for 2 minutes. It's very important. Actually, this type of questions they will ask in the advance only. In the mains, one time only, just one time only they ask. A get cancels. So here dy by dt is a great okay growth of I. Dy by dt into density and area is get cancelled. A and let it files. Which is equal to k into theta divided by pi. Okay, now in this case, now growth of ice becomes dy by dt is a growth of ice becomes k into theta rho into L ice. Don't by heart this formula. Don't try to by heart. It's difficult. The method only you should know. Okay, the student has to by heart. While teaching, okay, for a teacher not required. Now here theta is the outside temperature or the atmosphere temperature. Atmosphere temperature. Rho is the density of water. L ice is the latent heat of ice. K is the thermal conductivity of the ice. Is one of the important case the thermal conductivity. Okay, if anybody have doubt, you can raise the hand. Okay, I will end the meeting now.